but sorry we're late getting started with it. First, about the math team, they are meeting every Monday afternoon at 3 and on the Birmingham West Campus, C100, and then again on Fridays at noon on same place. Okay. If you want to meet on this campus my office hours, you know what they are, and as long as I can make it for them. Right now I'm running sort of low on energy, though today's been the best Monday I've had since I started treatment. So, but we'll see how it goes toward the end of the day. I was able to be in on time today and that type of thing. I do have a meeting coming up on February 22nd. That's this Thursday, I believe it is. It's a training type thing that they have for us, and again, if I'm up to it energy wise and they have room in the, I have it reserved, registered for it yet, because I wasn't sure if I'd be able to make it. I didn't want to take a seat if somebody else needed the training, but that's 2 to 3:45 on Thursday, so I'll be out of the office then if I'm able to be here. Now, this is something not so much, though you can use it for sure if you need it, but this would be something more that if you want to participate in it, you would be ideal candidates to do so. It's the tutoring schedule. On this campus, we have 2 major places for tutoring. One is Student Support Services just down the hall here in room 202. And there I know that Miss Cicely Martin has hours that she is tutoring. She's one of our instructors here, and she would be a great tutor for any course you needed. Okay? So you'll have to check her door. Her office is just past 205 on the left going down the hall. There's 2 little offices between there. Hers is the first office. It doesn't have a specific number. Or you can check in room 202, which you get to before you get to her office, and it's on the right. It's just across from the second stairwell going downstairs. But if you'd like to tutor, check with them and see. They pay you to tutor. So check with them and see if there's any times that will fit and needs that they might have for you to tutor, because she can't tutor all the time because she's teaching as well. And some of her classes are on the Birmingham campus, so there's, I'm sure they have plenty of need for tutors. And they may have more than one tutor at the same time if they got lots of students there to be tutored. But if you need tutoring, which I doubt, but there's let's see. The second place for tutoring is downstairs in the Space Center. That second stairwell that I was talking about that goes downstairs right across from 202, if you go down a complete flight of stairs to the middle stairwell and then one more, 2 half stairwells down, as soon as you walk out there, hang a immediate right and just twist around and you're right there at the Space Center. That's the second place we have tutoring on this campus. And right now, they only have tutoring there Mondays and Tuesdays. I'm sure they'd like to expand that schedule, okay? On Monday, they have a tutor for math from 12 to 4, but that's only for developmental math. You guys and gals who aren't here, but you would be able to tutor anything up to Math 125. So they may be looking for tutors there. And like I said, that's only from 12 to 4, and he's only developmental. That's on Mondays. On Tuesdays, they do have a math tutor there from 10:30 until 2:30, all math levels. That's Mr. Means. So I guess he can cover anyone coming in then. Wednesday, Thursday, Friday, they have nobody, okay? And like I said, I'm sure they would love to have to fill in the gaps there. So, and they pay as well. I don't know what the rates are or anything, but you do have that. Now, are any of you also Birmingham students. You are, okay? They have tutoring on the Birmingham campus. Now, in Birmingham campus, there's 3 possibilities for tutoring. I think it's mostly SSS tutoring that is in the SSS lab there, which is in C106 maybe, or something like that. When you enter the C building from the B building side, the very first door on the right is the SSS, Student Support Services Tutoring Lab, where they have a professional tutor, Mr. Harris, but I think also they probably can use some student tutors. I don't know, you can check on that. Then in B118, which is the STEM lab, they also do tutoring, and you can check with Mr. Dr. Briggs on that. I know that they have hours set up for tutoring there too. And that's for beyond SSS, you know, beyond developmental. And then they have a space center also, and that's in the Leon Kennedy Center, the student center there, and that's up on the 2nd floor. The space center, kind of across the hall from the bookstore there, okay? Now the free tutoring schedule on that campus in the space lab, they have a lot more coverage than we have here. They have all 5 days of the week covered. They don't have all the hours of the days covered. For instance, developmental math, they have 8 to 9:30, but they don't have any higher level math. 10:30 to 2, they have all levels of math. And from 2 to 4:30, they don't have any math covered. On Tuesday, they have developmental math covered only from 11 to 12 and 1:30 to 5, but they have no upper level math coverage all day long. So they can certainly use somebody there. Wednesday, developmental math 8 to 9:30. All math levels from 10:30 till 2. Developmental math from 1:30 to 5. And developmental math again 11 to 12:30. So again, they don't have good coverage there for upper level math except 10:30 to 2. So 8 to 10:30 or 2 to 5, they certainly look like they could use some upper level math tutoring. Thursday, developmental math from 8 to 12, all levels of math from 10:30 till 2, developmental math again from 1:30 to 5, and that looks like that's about it. So they look like they could use higher level math tutoring from 8 to 10:30 and from 2 until 5. On Fridays, they have developmental math from 1:30 to 4 and all levels of math from 10:30 to 12:30. So from 8 to 10:30, they don't have any higher level math coverage, and from 12:30 to 5, they don't have upper level math coverage. So you can check. Dr. Davis handles the space lab on both campuses, so you can contact her. Dr. Briggs, the STEM lab on the Birmingham campus, West campus, and then Ms. Harris and, Ms. Hollins, I think, handle the tutoring on this campus, SSS tutoring. All right. Okay, that took a little longer than I intended, but I wanted to get the word out if y'all do need some help. Okay. Let me turn over. If you can help, is what I meant to say, with the tutoring, or if you needed help in tutoring as well. Okay, while that's coming up, we did get as far as, I'm pretty sure I've tried to erase this and evidently didn't get it erased well. It was testing Wednesday afternoon and it didn't erase well, so I'll try to clean that up later. we're starting today in 2.2, page 115, derivatives of sine and cosine functions. But before we pick up there, did want to see if there are any questions. You indicated there might be some.
I was hoping that you could work 23 and 24 from 1.4.
1.1?
1.4.
1.4. Okay, my hearing's not good. Okay, 1.4. And was it 20 and 21?
23 and 24.
23 and 24. Okay, good deal. All right, now this may not be the best slide to do it on. Let's see, yeah, that has a little more room there. So this is page 83. Let me get my pen situated. Page 83, 1.4 exercise. And 23 is the first you said?
Yes.
Okay, 23. All right, this says, in these exercises, find the limit if it exists, and if it does not exist, explain why. Okay? So 23 is the limit as x approaches 1 of f of x, where f of x is a piecewise defined function for x cubed plus 1 anytime x is less than 1, and x plus 1 anytime x is greater than or equal to 1. Okay.
What does that mean? What is it?
All right. Okay, what a piecewise defined function is one that for part of its domain it has one definition, like for all x is less than 1, it's x cubed plus 1, but from all x's from x equal 1 to the right, to positive infinity, it's just x plus 1. So it would be something like, this is a realistic example, but if you this is really a dumb example, but if you had a short-term loan, they're going to charge you interest at x cubed plus 1, that's anything less than 1, but if it's a longer term, they're only going to charge you x plus 1. So you have things like that. I mean, phone plans or other things that are, one sort of circumstances if you use less than so many minutes, another sort of circumstances if you use greater than a certain number of minutes. That's what that represents, okay? So we're wanting x to approach 1, and we're to find the limit of that. Well, 1 is a turning point there. We don't know what's happening there. So what we have to do is x is approaching 1 from the left-hand side, we look at this function. And from the right-hand side, the positive side, we look at this function. So let's look at each of those separately. Now, do you want me to write them out, or can you do that sort of in your head? Okay, so what is this one as x approaches 1 from the left-hand side? What is that going toward?
2.
2, okay? Now, it never gets there because this is less than 1, but it's approaching 2. That would be its limit from the left. How about the second one?
2.
2 also. Well, since its limit from the left and limit from the right are the same, then its limit is 2. So that limit would be 2. Does that make sense? All right, good deal. You wanted 24 as well?
Well, yeah, that's what that one would just be the limit.
I'm sorry?
That one would just be the limit from the left.
Yeah, we're not even interested in the limit from the left because that has a little plus there. See, number 24 is written this way. The limit as x approaches 1 from the upper side, the right-hand side, from the plus side, 1 from the plus side. I mean, it's plus on either side, but from greater than 1. At least I think. My eyes are not good. I think that's what it says, of f of x. And here, again, it's a piecewise defined function, and this is f of x equal to, for x is less than 1, it's just x. For x less than 1, which this isn't even asking about, okay? And 1 minus x anytime x is greater than 1. Okay? So this is approaching that. So in reality, who cares about this one for this problem? Because this is x approaching 1 from the upper side. Oops, I left off my equal, didn't I? Not that it really matters that much. Oh, actually, the equal sign is with that. Interesting. A little screwball in there, okay? Okay, but it really still doesn't matter, because that's as it's approaching x from the left, from the lower side. That would be going to 1. But who cares? We're looking for the limit of f of x as x is approaching 1 from the upper side. And what would that be? 0. From the left, it would be 0. Now, if they left this off, then you would include both of them. From the right would be, from the left would be 1, from the right would be 0, so that wouldn't have a limit as x approaches 1. But as x approaches 1 only from the upper side, that would be the 0 part. Does that make sense? All right. Tyler? Okay. How are you feeling? Good. Excellent. There you are. Okay. And by the way, did you get the first test? Okay. Before you leave today, pick that up. Okay. And what was that?
Number 40 from 1.5.
1.5, number 40. Okay. I'm answering some questions that came up because of the test, so you haven't seen it. But in fact, let me go and give it to you so you'll see which ones these relate to. Well, there, I think I found it. Yeah. That's my key. My original there's the copy.
Thank you.
All right. And as I told the others, I can clarify anything on the test. If you have a question, what does this mean? What are you meaning here? Whatever. But I won't do any from the test, but I will do anything from the book that's similar to the ones on the test. So that's what we're doing now. Okay? And I guess that first one was similar to which one?
Number 4 and
Number what?
Number 4 and number 8.
Number 4 and 8. So these were similar to those, okay? And the 1.5 is which?
Similar to number 10.
Huh?
Similar to number 10.
Okay, and what's number in 1.5? Number 40, okay? All right, so this is page 92. Can I go on and erase this? Tyler, do you have what you need from here? Okay. And you can go back and see it later. It will be recorded. So let's erase that. And this is page, you said number 40, page 92. This is 1.5 exercise. And this is number 40, he said, right? Okay. Sorry. And these are finding one-sided limits, similar to what that second one we just did. In these exercises, find the one-sided limit if it exists. So number 40 is the limit as x approaches negative 1/2 from the positive side. Okay, lots of parentheses and things that make it really confusing looking in there, and plus and minus signs. And here we have 6x squared plus x minus 1 divided by 4x squared minus 4 minus 3. 4x minus 3. Right? All right, I believe I got it. Okay? Now, what's your first approach on a problem like this? This is one that we call a rational function. What's your first approach on a rational function?
Try to factor.
Factor everything in sight. Absolutely. Okay? So let's see if we can factor that numerator. Okay? So I'm going to try to unfoil it if I can, and we'll also try to factor the denominator if it's factorable. They may not be factorable. Now, in doing the numerator, what are some possible factors? That unfoiling is taking them apart. What are some possible factorizations of that first term here? There's several possibilities. Come up with one.
2 and 3.
Okay, 2x and 3x, right? Okay, let's do it in that order. 2x and 3x. Okay? Now, where I look next is the sign of the last term, which is,
Negative.
and what does that tell us?
They must have a positive and a negative.
The what? A positive, one positive, one negative. Do you have an inkling which it might be, or you want to just do it trial and error? Either way will do. Huh?
The 3x should be positive.
Okay. Okay. I know what you're thinking, but we'll do it. Okay. Now, Tacoma, right? Okay. All right. And did get a copy of the first test? Okay. Good. All right. Okay. And what's the only possible factorization of the last term? 1. This is a real tough one. Oh, 1 times 1. Okay, yeah, we can handle that one. Okay, but before we proceed, always check and see if your factorization's right. Okay? So now we're going to foil it. We unfoiled to get here. Let's foil it and see if we get what we are supposed to have. 2x times 3x. 6x squared, check that one. Then the outer, 2x times 1. Positive 2x.
We have negative 3x.
Negative 3x, that would give us?
That's backwards right there.
Negative x. Okay, now, what's wrong with this picture? We got the right coefficient, 1, but we have the wrong sign. So if we have the right coefficient but wrong sign, just change the signs. Okay? So what we'll do here is change that to the minus and change this one to the plus. And then you can go back and check again just to make sure. 2x times 3x is 6x squared. Minus 2x plus 3x will be plus x. Minus 1, yes, we got it. All right? Now, I should probably have an equal sign in here. All right, this isn't the limit. This is just a factorization. Now, here's where I cheat, okay? I'm always looking for the easiest way to do the problem. Possible factorizations here, I know that 3x will not go into 4x squared. 2x might. So I'm going to hope that 2x plus 1, and that should go here too, might be the factor here. So I'm going to just put it down, okay, 2x plus 1. What would be the remaining factor if that were the factor? How would 4x squared factor if one of the factors is 2x? The other factor would have to be 2x, okay? And how would that minus 3 factor if one of the factors was a plus 1? Minus 3, All right? Now, that's how I hope it'll factor. Let's see if it will. Okay? 2x times 2x. 4x squared. Check. Okay? Then the outer, minus 6x. The inner is plus 2x. So adding those two together would give you negative 4x. All right, that's looking promising. And then the last term is negative 3. We got it. Okay, so that worked. Now what do you notice? Ah, yes. The 2x plus 1s divide away. Okay? So now we're looking at the limit as x is approaching negative 1/2 from the positive side of just simply 3x minus 1 over 2x minus 3. And how would you evaluate that limit? Like Glade. Plug it in, plug it in. And what would that give you? Three times a negative 1/2 minus 1 over 2 times a negative 1/2 minus 3. And what would that be? Negative 3/2 minus, how many halves is 1? 2 halves. Okay, over, and what's 2 times negative 1/2? Negative 1 minus 3 would be negative 4. So this will be a minus 5 halves in the numerator and a minus 4 in the denominator, and that would be minus 5 halves times, flip it, minus 4 over 1. The 2's, well, the minus signs go away, or multiply to be positive, and this would be 10. If I did it right, that does seem to have a limit of 10. Whether you're approaching from the left or the right, okay, it works. Is that the value of this function there? No, because it can't equal negative 1/2 there. That would give you, that's an indeterminate form, so you do not have a value at x equal negative 1/2. But either approaching from the left or the right, they're both approaching 10 at that value. Okay? Does that make sense? All right. Good deal. Does that answer what you need? Okay. Any others while we're here? Okay. If not, let's go on to, let me clear what we got here. Is that all right? Everybody got what we got here? All right. Here is Cheston. Okay. It's almost every other student is here. Okay. 7, yeah. Okay. Now, what we've done so far today is answered questions from Chapter 1 that were similar to test questions. Okay? Okay. All right, to clear this? No, okay. This is problem 40, exercise 40 on section 1.5 on page 92. Earlier we had done 2 from 1.4, which were similar to other test questions, but you'll be able to pick them up off the YouTube videos, right? They won't be up there for a while. It usually takes them a couple hours to load to YouTube, and then I've got to put it in the playlist, so that's probably the longest delay. Okay. So, any more questions from Chapter 1 or elsewhere? Okay. And let's pick up where we left off in Chapter 2 in Section 2.2, derivatives of the sine and the cosine functions. Now, up till now, we've been doing a few different kinds of functions. One was polynomial functions. Really nice, easy derivatives to take. Okay? Then we extended that to power functions, which were very similar to it, but then you run into a few problems with domain issues. Okay? And then after that, there were a few others we did perhaps, but now we're moving into a couple of trig functions, sine and cosine functions. All right? So just jump right into it with a theorem. Now, this almost seems, really? Okay, is it this simple? Derivative of the sine function is the cosine function. And derivative of the cosine function, not quite so easy. All you have to do is remember it's a minus of the sine function, the opposite of the sine function. Boy, pretty simple, right? Now, where does this come from? I don't know if they're going to do the proof on the slide or not. No, they jump right into example 8. Now, the proof is underneath that, and it looks like sort of a little bit on a complicated side, but I'm trying to remember. It seems like we have hit what you needed, but maybe not. Let me go back and refresh my brain here on whether we did that or not. So this is the first time I've taught from this course, and from this text, and I don't recall if this book has already covered this or not. I'm guessing not. Okay? But I thought we had. Go back to the yes, I think we did. I knew most books did. Nah, maybe not. When we were doing the limits back in 1.4, or maybe earlier, we did introduce a couple with signs in them. Here we go. 1.3 actually. Yes, I thought we had. Yeah. And I think you may even have one or two on the test this way. Okay? Remind you to go back and look on page 69 on theorem 1.9 in section 1.3. The limit of sine x over x is 1. The limit of 1 minus cosine x over x is 0. There's a couple of those indeterminate forms with the trig functions that do have limits. And they use those two in doing the proofs below here. If you'll, on page 115, when you look at that proof, when they get down to the point where it's about midway through the proof, the limit as delta x approaches 0 of cosine x times sine delta x over delta x, that limit we know to be 1. Okay? And 1 minus cosine delta x over delta x, we know that limit to be 0. They use that in the next two steps, and that's how you get the derivative of sine equal cosine. Okay? Now, the other thing I wanted to do for you maybe too, is to approach it from this respect. I think the book does this too, and I just lost my page. There I am. I wish they showed this figure, but they don't, so I'm going to draw it. Okay? Can anyone tell me about what a sine function looks like? Give me a few points to plot anyway.
0 is going through 0.
Yep, 0, 0. And then I'll pick a x value, pi halves. What would the pi halves be? 1, exactly. It's going to be up here. And at pi, it's going to be 0 again. And 3 halves pi. 3 halves pi is going to be a negative 1. Somewhere down here. And then 2 pi will be 0 again. Okay, very good. If we went backwards to negative pi halves, what was its value there? Negative 1. Okay. Now, I'm not going to do much more to this, but something like that. Now, what does the derivative tell you?
Slope
Of what?
of any point on there.
No, well, actually, the slope of the tangent line at any point on there. Okay? Now, at 0, what appears to be the slope there?
Positive.
Positive. And about what value? What is that? Almost the same. If you sort of take out this part, what does that look like it might be?
45 degrees.
Yeah, a line going through 45 degrees. Does anyone know what function that is? Huh? No, okay. You're thinking right, but simpler than that, okay? This portion right here almost looks like a straight line, doesn't it? And that straight line would be f of x is equal to, say again? 1/2. F of x equal 1/2 would be a line that's like that. This is f of x equal, yeah, 1x, exactly. Slope of 1, y-intercept of 0. F of x equal x. And what's the derivative of that? Say again?
0.
No?
1.
1. 1 times 1, x to the minus 1 is, x to the 0 is 1. That would be 1. And that's why, okay, all right. Before I got too far here, let's draw, give me a different color here. Red, okay. All right. Let's do the cosine function on this same graph. Where does cosine begin? Okay, it begins at 0, it's 1, and then it goes down to 0, then it goes to minus 1, then it goes up to 0, and then up to 1 again, and going in the opposite direction, it goes down to 0, and blah, blah, blah. So here is the cosine curve, right? Ooh. Got my peak kind of off here. Okay. So it's going to mess up my whole drawing here, but all right, let me sort of clarify that a little bit. Okay, something like that. I don't draw very well. Okay? So, derivative of this function is 1, and that happens to be cosine of 0, isn't it? And what is the derivative of this function up here? Sine x at pi halves?
0.
0, okay? And that happens to be the value for cosine x, isn't it? And what appears to be the derivative of this function, of the sine function at pi? Negative 1, and that is the value for cosine function. And then the value here would be, derivative here, at 3 halves pi, sine of 3 halves pi would be, I'm rubbing the skin off my fingers here, somebody help me.
0.
0, okay, and that's what cosine is. And going back this way as well, 0 is, yeah, derivative of sine is cosine. or at least it appears that would certainly make sense. Okay? Now, how about derivative of cosine? What would the derivative of cosine be here at 0? Derivative of cosine at 0?
0.
0, and that's what sine is, right? What appears to be the derivative of cosine at pi halves? Second?
-1.
-1, but the sign is +1, so that lends itself to be the minus sign. And down here, derivative appears to be
0.
0, and sine is 0, or -0, it doesn't matter, it's still there. And here it would be what appears to be the derivative here? +1, but the sign is actually -1. So it's the opposite of sine. So sure, that looks like from their graphs, that looks like that would be a logical, and in fact, when you do the proof there and use those sine x over x and 1 minus cosine over x, yeah, you find out that's exactly what they come out to be. Make sense? All right. Now let's go to example 8. All right. Jumping right into it here. If your function, I hate when they do this. Okay. If your function is y is equal to 2 sine x, what do you think the derivative would be? Y prime would be 2 cosine x, exactly. This is just a constant, and then derivative of the sine x would be cosine x. Ha! Pretty nice, huh? Let's look at the B one. If your y is equal to sine x over 2, well, the good way to do that is pull that 1/2 out front, make it a coefficient. 1/2 of sine x, what would be y prime?
1/2 cosine.
1/2 of cosine x, or cosine x over 2, if you wanted to get it back looking like the original function. Very good. Pretty nice, huh? Okay. Let's look at the C one here. Here, y is equal to x plus cosine x. Can we do that? Sure. This is addition subtraction rule. So what would the derivative be?
X minus sine x.
1 minus sine x. Derivative of x is 1, and derivative of cosine would be minus sine x. Excellent. Excellent. Okay. Okay, we got more x's in there. Let's look at the D one here. Okay. Here we have y is equal to cosine x minus pi thirds times sine x. So what would y prime be? Derivative of cosine is negative sine x. There we have it. Okay, why would you change that? It's just a coefficient, right? Negative pi thirds cosine x. Perfect. Okay? He's trying to get a little advanced on us. You do that later with the chain rule, but we're not in chain rule yet. And it wouldn't be appropriate here anyway. That's just a coefficient. It's a weird looking coefficient, but it's just a coefficient, no weirder than 1/2, except it's got an irrational number on top. So it just carries it along. Okay? Any questions on that? You see why that's true? Wait, yeah. You see why it is? Not? Okay, probably 3, right? Okay, let's see if they have, oh, I thought there was an E. No, there's not. Okay? Whoa. That's our sines and cosines, folks. That's all. Okay? Now we're moving to, on page 116, rates of change. Now, what do rates of change mean to you? Anything special?
How fast something is changing?
Okay, how fast something is changing. Yeah, the rate of change. Okay? And thinking kind of mathematically, maybe even say again? Yes, exactly. The rate of change is going to be something very much like a slope. And what do you guess it might be? The slope of what? The tangent line. And what is the slope of a tangent line related to? What's a good answer in this course? Yeah, take a derivative. That's what it is. Okay. So you have seen how the derivative is used to determine slope. Yeah, there we have it. Derivative can also be used to determine the rate of change, which is a slope, okay, of one variable with respect to the other. The applications involving rates of change occur in a wide variety of fields. Anyone want to suggest a few? Say again? Physics! Excellent choice there. I mean, if there's another good answer, physics is going to be a good one, okay? Here's my take on what physics is. I was a physics major as an undergraduate. I always looked at it this way. Math is still, the building blocks of just about everything, science-wise anyway. And physics is applied mathematics. Okay? And then, when I got into college and stuff like this, I saw that engineering is applied physics in just about every area. Now, biomedical engineering, you're doing other things with it too, but you're still applying, it's applied physics. So you're just applying one to another to another. So the derivative can also be, the applications involve a variety of fields, physics, engineering, enormous astronomy, there's just anything, economics. You worry about the stock market changing, or the GDP changing, or other things. Anytime there's a change occurring, that's going to apply to rates of change. A few examples are population growth rates. That's a change, isn't it? Production rates, business, industrial engineering, right there. Water flow rates, hydraulic engineering, okay. Velocity, acceleration, definitely physics type things. And, I mean, these are just a few. My wife is an epidemiologist, and they are concerned with rates of disease advancement. So they use it too, even though they have very little, generally, calculus or physics backgrounds in it, but they are still using the concepts, whether they realize it or not. Okay? A common use for the rate of change is to describe the motion of an object traveling along a straight line. Now, how would you describe the motion of something? Like if I push this chair along a straight line, what are some things to describe about how that's moving? Say again? First, you have a change of position. And how long did it take you to change that position? Some time. So, the change of position divided by the time would be its
Rate of change.
The rate of change, also called the speed or velocity. Now, if you notice when I pushed it here, it started off fairly fast, and after a while was slowing down, so the rate of change of the speed was, yes, going down. So then you would say it was, what's another term we would use? Decelerating, yeah, it was accelerating with a negative acceleration. You're absolutely right. You have to physics that, okay? So, here we see that objects moving in a straight line, we talk about position, we talk about change of position, which will relate to velocity or speed, and we'll talk about change of velocity or speed with a term called acceleration, okay? And then there's other things we can do. How did I make this move? Pushed it. And what is a push or a pull? A force, exactly. So their forces are related to change of motion of an object in a straight line, or in curved lines or other things as well, curved shapes. Okay. In such problems, it is customary to use either a horizontal or a vertical line, depending on whether you're doing horizontal motion or vertical motion. I could have said, let's drop something from up here, and then it's going to fall in a straight line, singular motion, okay? With a designated origin to represent line of motion. On such lines, the movement to the right, or upward, or downward, or to the left, wherever, is considered to be in the, to the right or upward is positive, and to the left or downward is negative directions. Just like our good old Cartesian coordinate system, right? That's what we base on. Now, occasionally, I won't even go there. Yeah, okay. The function S, okay, interesting, that gives the position relative to the origin of an object as a function of time is called the position function. Now, often we use other things like X or Y or other things, but S is a perfectly good position function name as well. If over a period of time, that's a delta t, time interval, difference in times, time interval, delta t, the object changes from an original position, S of t, to some new position, S of t plus that little bit of time, then this becomes your delta S. Then, by the familiar formula, rate is equal to distance over time, we have the average velocity is delta S over delta t. Right? If you're driving from here to Tuscaloosa, because it's close, for you Auburn fans, I'm not trying to be, pick on that, but it's just close here. The change of distance here is what, maybe 55 miles or something? I don't know, it's whatever it is. And the time it would take you to get there, divide the change of position by the change of time, that would be your average velocity it took you to get there, right? Pretty much straight interstate that way, so you don't have to stop and go as much. I would have said Birmingham, but it might be different ways to go there. Okay, but there is average velocity. Delta S over delta t. Change of position over change of time. A rate of change. A billiard ball is dropped from a height of 100 feet, that way on up there. The ball's height at any time t is in this position function. Okay? S is equal to minus 16t squared plus 100. Where did they get that? Any of you had some physics? Say again?
32.
Okay. The acceleration due to gravity is 32 feet per second squared, and this is 1/2 of that, but it's downward, so that's going to be minus 1/2 of 32, which would be minus 16. But where did the 100 come from? The initial height. When t is equal to 0, your position is at 100. The ground down here is going to be your 0. Okay? So yeah, that's where that came from. You don't need to know that for a math course, but it makes sense. It's not they just threw it on the board here. Oh, we'll just say this. Okay, no, that really comes from physics. Where S is measured in feet, that's why they use the 16 rather than 4.9. That would have indicated meters per second squared. Okay. So where it becomes 9.8 meters per second squared, and half of that would be 4.9. Where S is measured in feet and T is measured in seconds. Find the average velocity over each of the following time intervals. From 1 to 2. What would be its average velocity? How would we do that? Anyone help me? Okay. This might be helpful. I hope it will be. Let's go back a little bit. We would need to do delta S, which is S of t plus delta t, minus S of t, and divide that by delta t. So what might be the first thing we would do here? S of, you're going from 1 to 2 seconds. Your t plus delta t would be? 1 plus 1 is 2. Okay? High level math today, right? Okay. So it would be S of 2, that's your t plus delta t, would be minus what? Times?
1 squared.
Second?
1 squared.
2 squared. Because that's what you're plugging in here, right? Okay? It'd be 4 plus 100. And that would be?
164.
Okay, only it's a minus.
Oh, it's gonna be 36.
36. Perfect. And S of 1, that's your S of t, that would be negative 16 plus 100, and that would be?
116.
Say again?
116.
That's a minus again.
Oh, yeah. So that's 84.
84. Okay. So your interval, the change of displacement during that time interval would be, your delta S would be S2, S of 2, which would be 36, delta meaning difference, minus 84 over the time interval, which was 2 minus 1, 1. So that would be a minus 48 feet per second, because your S was measured in feet and your time was measured in second. Looks like that would be minus 48 feet per second. Average rate of change over that time. Well, let's go to the smaller time interval from 1 to 1.5 seconds. Boo hiss. Here your second S of t plus delta t, is going to be 1.5. What would that be? Looks like time for a calculator to me. Minus 16 times 1.5 squared, I think is 2.25, isn't it? Plus 100. This is where the calculator comes in. Minus what? Well, that's not too bad. 32 plus 4 be minus 36. Is that right? Is that right? That would be 64 feet. S is in feet. I should have maybe put the units here too. So then our average rate of change would be S of 1.5. Did I do it right? You punch it. Okay, good. So that would be 64 minus, and the S of 1 is still the same, 84 over, but what's our difference here? 0.5, and that's 84. My writing stinks. Okay, and that would be a negative 20 over 0.5, which would be a negative 40 feet per second, right? Okay. What if we only went 1.1 seconds later? Okay. What is your S of 1.1? That would be minus 16 and 1.1 squared plus 100. That would be negative 16. I think that is 1.21, isn't it? Plus 100. So that would be negative 12.1 plus 100. Yuck. Okay. And that would be, what, 87.9? Oh, goodness. What is it? Okay, no, that's a minus and that's a plus. Minus 12.1, I think it is. Oh, that's a 16. Where is it? Oh, yeah, wait a minute. Yeah, you're probably doing it right. Goodness gracious. Let me. All right. I can't read my own writing. Okay. Minus 16 times 1.21. What would that be? You probably were doing it right and I wasn't. $17.21 plus 100. What'd you say, 82.79? Okay. And subtract, okay, from that, the 84, because that's your 1. F of 1, S of 1 was still 84. So that comes up being what? 1 point second? Wait. Say that again. Negative 1.21. But divide that by what's your delta t now? 0.1, 0.1, and that would be minus 12.1 feet per second. No, is that right? I think something's wrong here.
Minus 16 times 1.21 plus 100, I'm getting 80.64.
Okay, let's go back. Let me get, I'm trying to do things in my head and that's not working too well. So let's back up and see. Okay, back me up and see 16 times 12.1, negative 16 times, well, I'm sorry, 1.21. Was that 17 point? Yeah, that sounds right. Plus 100 would be 82.79, is that right? Minus 84 is that indeed? It seems right, doesn't it? But it seems like way too big a drop. What did you get yours to be? Second?
80.64.
80.64? Where? Up here? Okay, but what is it? Is that the...
It's negative 16 times 1.21 plus 100.
That gave you what?
80.64.
Okay, that may be better. I don't know where my error came in there. So let's... Okay. 80 point, what say? 64?
Yes.
Okay, and then 80.64 minus 84 is going to be 3.36. Is that right? That sounds better. Negative 3.36. And then when you divide that, then you're going to get 33.6. That looks like more in the chain here. Negative 4.48, negative 40, negative 33.6. I don't know, we may have just made an error somewhere there before. Okay. Now, look like that might have a limit somewhere. I'm going to hazard a guess here.
0.
I won't be that low. About minus 32. Hey, that may work, mightn't it? Because the change of velocity over change of time is acceleration. And what is acceleration? Acceleration due to gravity is? 32 feet per second squared. So I bet you that is going to be, the limit would be 32 feet per second squared. Negative, okay? What's that?
Gravity is always negative, correct?
Yeah, well, yeah, if you're counting downward negative, yeah, that would be minus 32. So sure enough, I think that fits the pattern a lot better. I don't know where I made the error before, but probably my lousy writing contributed big time. You see how that happened? Okay, sorry if it's my errors in thinking and stuff are screwing it up. Okay, and they got negative 33, they got negative 48 feet per second, negative 40 feet per second, negative 33.6 feet per second, and sure enough, if you had continued. All right, now, okay, here's where they show it. For the interval from 1 to 2, the object falls from a height of s of 1, would be 84 feet. That's where it was at 1 second, and at 2 seconds it was down at 36 feet. So its change of height there was a negative 48, 36 minus 84, and the time interval was 2 minus 1, which is 1 second, so it's minus 48 feet per second. That's the average velocity, okay? But if you had a shorter time interval from 1 to 1.5 seconds rather than 2 seconds, then its s of 1.5 was negative 16 times 1.5 squared times that, and they didn't show the math, but it came out 64 feet, and 64 minus 84 is minus 20, but then your delta t is 0.5, so that would be minus 40 feet per second. Good for them. Next time s of 1.1, yeah, and there's where we made our error. 1.21 is 1.1 squared, and I just didn't do the math on it, but when y'all did, and you got that to be 80.64 feet is the s of 1.1. Subtract that from 84, you get negative 33.6. Negative 3.36, divide that by 0.1, you get negative 33.6 feet per second. Note that the average velocities are negative, indicating the object is moving downward. Surprise, surprise, okay? And then, in general, as s is equal to some function of time, the position function, that's the position function of an object, moving along a straight line, the velocity of the object at any time t is going to be the limit as that delta t approaches 0. Those were all average velocities, average speed, but then if you let the delta t get closer and closer to 0, you're going to have your instantaneous velocity, v of t. That'd be s of t plus delta t minus s of t over delta t. Good old derivative formula, right? Alpha x plus delta x minus alpha of x over delta x. Yeah, that's your first derivative. So let's go back and see what was our s function again. Ah, there it is. I'm going to erase this for now. I could have erased everything, I guess. Okay, only need this. So what's our s prime? If that is indeed the velocity, negative
Negative
32 t. Very good. And if t is equal to 1, that would be negative 32 feet per second squared. Wow, I threw that unit in on you. No, feet per second, sorry. Feet per second. Okay. Whoops. Erased too much. Feet per second. Okay? And that did appear to be where that limit was going. Well, actually, that was on this slide. Toward negative 32 feet per second. Because you're evaluating at 1 second. That's why it's the same as your acceleration. Okay. So that's your S prime of t. In other words, velocity function is the derivative of the position function. Now, velocities, as we know, can be 0. They can be positive. They can be negative. They can be any one of those values. The speed of an object is the absolute value of its velocity. Speed is not negative. It could be 0, but most of the time is an absolute value of your velocity. Okay? So speed we call a scalar quantity. This is not in your math book for those who are taking physics because it's doesn't relate to direction. But because velocity can be positive, negative, or 0, that is more of a vector quantity. And the sign there, especially if you have motion in one dimension, indicates which direction you're going. Okay. Sorry, that was extra. Okay. The position of a free-falling object, neglecting air resistance, under the influence of gravity alone, and that's what we mean by free-falling, can be represented by this formula. And this is the one I was referring to earlier. It's S of t is equal to minus 1/2 gt squared plus v0t plus s0. And remember before, we started out with a minus 16 t squared, and that was because in feet per second in the U.S. customary system, g is minus 32, or 32 feet per second squared, 32, okay? You put the minus here because it's always negative. In that problem, we didn't have a t term. Why? Remember the problem we had back here? A billiard ball dropped from the height. I'll go on and erase this so all the stuff won't be in our way. Dropped from a height of this, that is position function. I see the t squared term, and I see a constant term. I'm missing the t term. Where is the t term? That v0t. Notice what it says. A billiard ball is dropped from a height of 100 feet.
So it's not thrown.
Not thrown. If you had thrown it, you'd have given it initial velocity. If you drop it, what's its initial velocity? 0. That's why we didn't see that term there. And then S0 was your initial position. And we already said that. That's where the 100 came from. Okay, so this is physics now. I'm sorry, I can't get away from it. Okay. Okay. Here. So there was our form. S of t, your displacement at any time t, is minus 1/2 gt squared plus v0t plus s0. Our previous example, the initial velocity was 0 because you released it from rest, dropped it, not threw it, okay? So that was 0. But 100 was your initial height, and 1/2 of g was your 16. Minus because it's going down. Okay. Now, that's your position function at any time t, and it could be any units you want to deal with. If you're using metric or SI units, you would have used g would be 9.8 meters per second squared. Okay? Just use it different. If you had been on the moon, that would have been about 1/6 of what it would have been here on Earth. If you're on some other planet, you just have to figure out what the acceleration due to gravity is on that planet. Anywhere on the surface of the Earth, it's going to be pretty close to that. Where S0 is the initial height of the object, V0 is the initial velocity of the object, and since we dropped it, that was 0, and G is the acceleration due to gravity on whichever planet or other celestial body you may happen to be. Most of the time on Earth, we take that to be 32 feet per second. Ooh! Oh yeah, they have feet per second per second. I was going to say they left out a per second there, but no, 1 per second over there, 1 here. And in physics, we usually do this. Mathematicians probably don't like it. We say that 32 feet per second squared. That's sort of a shorthand, feet per second, or 9.8. meters per second squared. Meters per second per second. You not really have square seconds. It's just, yeah. Okay, that's just the shorthand for it. That's the value for G on Earth. Moon, about a sixth of that. Mars, not as small as the moon, but bigger, but smaller than Earth, bigger than the moon. Okay, wherever you happen to be resting. Okay. So here's example 10. All right. Okay. Yeah. Time t equals 0 seconds. I would say this. Okay, never mind. A diver jumps from a platform diving board that is 32 feet above the water. They like 32s, don't they? Okay, in feet. Okay. Figure 2.21. Okay. Same in the book. Yeah. The initial velocity of the diver is 32 feet per second. Okay. Remember they said he jumped from there. So that's what gave him an initial velocity. Jumped. And notice what sign that is. Say again? Which means he jumped up. Yes, he jumped up and then came down. Okay? So that's why it's 16 feet per second. When does a diver hit the water? Okay? And then later we'll do what is the diver's velocity at impact. All right? All right, let's identify our parameters here. Time t equals 0, that's your initial time. So I'm going to call that ti equals 0. Okay? A diver jumps from a platform that is 32 feet above the water. So what would that be? And by the way, I use I. The book is using O for original. I like I for initial, but since they're using O, I'll use O. 32 feet would be what? S of what? Original position, right? So S of O. Like we did back here, S of O. That's it. Okay? All right. Initial velocity of the diver is 16 feet per second. So guess what that is? V sub O. Okay? VO. Okay? So, when does the diver hit the water? What's going to answer that question? When? What answers that question? Time. We're looking for the time. So this is what we're looking for here. What is the time? When does the diver hit the water? Well, where is the water here?
32 feet down.
Is 32 feet down, which on our scale here, so your what I'm going to call S final, if S original is 32 feet, what's the S final?
0.
0, because, yes, it's down there at 0. Okay? So now let's pull up our formula. That one right there, position function. And we'll say that S of t is equal to, how does it go? Negative 1/2. G, okay. T squared, I'll allow you to put that in there. G, T squared. What next? Plus V0 T plus SO. Yeah, I said 0, but if it's that thing there, I usually like to call it O for original. That's just me. You could say that's at time t equals 0, so that could be a 0 too. it's not clear which it is, but whichever you choose to call it. So what is your S of t, which is going to be your S final, some t seconds later when he hits the water? That is going to be 0. Okay. 0 is equal to negative 1/2. Now, what's your G here?
32.
Yeah, because we're dealing with feet and seconds. That's going to be 32 feet per second squared. That's the acceleration of gravity on the Earth, and we're assuming this platform dive is from the Earth. You know, we'll make that assumption here. What's next?
T squared.
T squared plus 16t plus 32. All right. So let's do the math here. Negative 1/2 of 32 would be negative 16t squared plus 16t plus 32 is equal to 0. Oh, they really liked you on this one, didn't they? What's the first thing you could do on that equation? All right, good deal. What would you factor? Negative 16. Let's get rid of that, and what would you have left? T squared. I pulled out the minus. Minus t minus 2 is equal to 0. Now what could we do? Say again?
I said difference of squares.
It's not quite a difference of squares, no. There's a couple things you could do. One thing, you could just divide out the minus 16, so you're through with that. Okay? And 0 divided by minus 16 is 0, so we don't have to even worry about that anymore, okay? Or you could just ignore it and then factor this and say, well, negative 16 is never 0. But so the next thing we're going to do is then factor again. T squared minus t minus 2 equals 0. How would that factor possibly? T minus
1 minus 1. 47.
Okay. Now, t squared factors is t times t. Got it? Right. Then we look at the sign of the last term, which is negative. What does that tell you about these two signs? One's positive, one's negative. Okay. Whoops. I shouldn't have a number in there yet.
That's definitely quote 16.
Okay. Now, what number goes with what? T minus 2 and t plus 1. Okay. So this tells you either what? I'm sorry? Okay, either t is equal to 2 seconds or negative 1 second. Okay, now, what would represent negative 1 seconds? He already gave you the test, right? Okay? We don't go backwards in time. Okay? So that one's immaterial for this problem. Now, what did that mean? That meant if the person was a really good jumper and jumped from here up and came down, it would have still worked the same way. Okay? Sure, if he'd have jumped up and gone right down in the water, it would have taken the same time. Surprisingly, but true. Okay. So, yeah, we're not going to go backwards in time. Okay. So that's out of the picture here. So when does the diver hit the water?
2 seconds.
2 seconds after each jump. Okay? 2 seconds after each jump. All right. Now, can I erase most of this and just fill in the answer? You got it? Okay. So this will be t is equal to 2 seconds after jumping. Okay? Now, what is the diver's velocity at impact? How do we get that?
Velocity.
And how do you get that? You start with the s function, which I hadn't erased at all. That was minus. Where do you want to begin it?
Minus 1/2.
1/2
You want to do G or 3?
g t squared VOT plus SO. That would be G was what?
32.
Yeah, 32 feet per second squared. So that would be negative 1/2 of 32 would be negative 16 t squared plus V0, remember, was 16t plus 32. Remember, that's when we started one from that we factored and did away with it. So, what is the diver's velocity at impact? Your v of t is equal to what? Okay, you want to go that far, or just do s prime of t? Since we're into calculus, let's just let it do the working, and we don't have to go back and do the deltas anymore. And what would this be? S prime of t would be there's your negative 32 t plus 16 plus 0. Very good. And that would be negative 32t plus 16. Now, when did he hit the water? Two seconds later, right? Okay, how'd you figure that out? Okay, s prime of 2 seconds would then be minus 32 times 2 seconds plus 16, and that 16 was feet per second. And by the way, the 32 is feet per second squared. Remember, that's what the g was. Okay. So this would be negative, second,
Negative 48.
when you add them. Okay, yeah. It's negative 64 feet per second, because this second, that's feet per second squared. One of the seconds go out with that, and this would be plus 16 feet per second, and that gets you down to negative 48 feet per second. I like to hang around with the units to make sure I've done things right. Yeah, his velocity just before he hits the water is minus 48 feet per second. Meaning he's dropping pretty close to 50 feet in a second. That's going pretty fast, right? Now, any reason that you think he would be going in like this then?
He doesn't belly flop.
Yes, a belly flop would then hurt like crazy, okay? And possibly even break a bone or so. The reason the hands are like this, to split that water, the surface tension of the water Otherwise, he could have either a concussion or possibly an injured neck, okay, if he had his hand by his side and hit the water head first. Not a good idea either. At that kind of speed, no. I think you better be doing that. Now, if you've noticed, now this is the Winter Olympics going on now, but in the Summer Olympics, when they have the swimming and diving, especially from the platform diving, what do you notice they're always doing to the water? Yes, there's some sort of current going in there breaking that surface. What you're doing is breaking the surface tension, because water has a pretty significant surface tension. Sounded like maybe somebody had experienced a belly flop before, and if so, if you can break that surface tension, it makes the pain a little less, okay? The other thing doing that does, water, if you're just diving into it, it's almost like a mirror. You don't even see it, but if you disturb the surface, they can pick up a little bit better the distance to the surface and stuff like that to come out of their spin or whatever they're doing. But you'll notice that, when, especially on high dives, there's always the surface being disturbed there. To break that surface tension, because at those kind of speeds, you can easily break bones, okay? Concussions and things like that, or have a terribly sore stomach, okay? Or other part of the body. You land on your back, yo, you're going to be feeling that for a while too. Okay, does that make sense? Now, velocity is positive when an object is rising, negative when it's falling. Notice that the diver moves upward for the first. Now, how did they get that for the first half second? How would they have gotten that? Well, we just figured that S of t, that is your velocity, v of t, which is S prime of t, is equal to minus 32t plus 16, right? Well, when you start off at t is equal to 0, what's his initial velocity?
16.
Positive, 16, okay? A fraction of a second later is going to be a little bit less, because he's slowing down. He jumps up, but then he starts slowing down. And when t is equal to, what will make this equal 0? 0.5, exactly. That's where they got for the first half second. So he jumped up for half a second and then went down for the rest of the time, which was 1.5 seconds. Now let's go back to that jumping off the side of the pool there, which would have occurred at -1 second. Jumped up half a second and down half a second. That would be 1 second later, wouldn't it? Hit the surface. Yeah. Makes sense. Okay. We didn't do that rigorously, but we did. I mean, we got it done. Any questions on that? All right. Let me erase. Well, let's see. I bet you they'll go to it. Yeah, here we go. Begin by writing the equation to represent the position of the diver, and that would be your position formula. How are we doing? Are we close to time? Oh, we are out of time. Okay. Let's just finish this. Writing the equation of position, that would be position function given as 32 feet per second, or 32 feet per second squared. V0 is positive 16 feet per second. S is 0 is, or SO is 32 feet. You can write S of t as negative 1/2 of 32 t squared plus 16 plus 32. And that would be minus 16 t squared plus 16 t plus 32. To find the time, let S equals 0. That's when he reaches the water. Solve for t. There's our equation. Factor out the minus 16, and they went on and factored the whole thing just like we did, and that gave us t is equal to -1 seconds, which we don't have. We don't have negative seconds, or 2 seconds, and that's the one we're going to use because it's after he jumped off the board, not before he jumped off the board. Choose the positive value, and then the velocity at the time of the derivative, plug in your 2 there, and you get minus 48 feet per second, just like you did. Very good. S prime of T, unit for, blah, 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 blah. Okay. Whoa, and that is the last slide in the section as well. So homework exercises here, 2.2. Do 5. It is both at calcchat.com and calcview.com. Do any of the odds 7 through 25. They're all at CalcChat, but 17's at CalcView. Finished, good deal. Do either 27 or 29. They're both at CalcChat. 27's at CalcView. Any of the odds 31 to 37. They're all at CalcChat. Only 37's at CalcView. 39 through 53. They're all at CalcChat. Oh yeah, you can put staples in. I forgot that. Okay. 37's at CalcView. I'm sorry. 43's at CalcView. Either 55 or 57. They're both at CalcChat. 55's at CalcView. Any of the odds 59 to 63. They're all at CalcChat. 59's at CalcView. Do either 65 or 67 or both. They're both at CalcChat. 65's at CalcView. And then exploring concepts, do either 69 or 71. Don't get too wrapped up with it, but see if you can do that. And then also 73. And then do any of the odds 75 through 79. All those are at CalcChat, but not at CalcView. Do 81. It's only at CalcChat, not at CalcView. And do any of the odds, well, do 83. It's a CalcChat, but not at CalcView. And if you get too bogged down, don't get too discouraged there. That's a little more involved. There's some true false that are given, 85 to 89. They should be at CalcChat. I don't know if they are. Finding rates of change, 91 through 93, either one of those. Both are at CalcChat. 91's at CalcView. Vertical motion, 95. Try to do that one. It's at CalcChat. Or 97. 95 or 97. And then they have some think about it, 99 through 99. Volume is a 101. Modeling data is 103. And then some applied problems, 105 through 109. Any of those. Do 111 if you can. And 113 if you can. They have a Putnam challenge there if you're interested in that. Okay, good deal.
I have a question.
Surely.
What does delta mean?
Difference.
So it's just short for...
Yeah, for a subtraction. Final minus initial. Change of S, delta S. Change of time, delta T. Initial time, final time minus initial time. That's your time interval. Delta S is final position minus initial position. That's your change of position.
So like, why were we using the deltas in the last section before we were like...
Yeah, because when you take a limit, the delta becomes the D, remember? D by D?
So that's the difference.
Yeah, it's a difference. That's exactly what it is. So actually, and we'll talk about this, I'm sure, in some applied problems later, whenever you see a problem that has a rate in it, or you just see the units, miles per hour, cubic feet per minute, or anything such as that, think of that. There's a derivative right there. Change of volume over change of time, where the time is a minute, volume is a cubic feet. And that's going to help you work problems like that just big time.
I'm not really that good at math. If I can start to reason it out in my head, I can sort of,
Yeah. Well, I try to talk through it that way, but sometimes probably I'm pretty obscure. So sorry. All right, good deal.
Yes, sir.
Appreciate your participation.